Hello everyone. In this video I want to talk about inspection in GD&T or for GD&T, and I mentioned it in one of my previous videos that if you see a dimension is put inside this kind of elongated ellipse, that's a sign for a dimension that has to be inspected. And when you see that percentage right next to the dimension, you can see here this 100%, that means this dimension has to be inspected all of the times. So you tell them how frequently the manufacturer part has to be checked, okay? And the important thing we have to keep in mind is basic dimensions will never be what toleranced and will never be inspected, okay? So they are never toleranced and they are never inspected. This is very critical. So if you want to do that in SolidWorks, so here you have this dimension, you want to inspect it, so you click here, right? And then you go down there. This top one is for reference dimension. This one is for the inspected dimension. So you put it inside this box here, right? And if you want, you can add more information to it, right? So if I click on this guy, it should ideally allow me to what? Allow me to add this line here and then say 100%. Okay, so now I know that dimension has to be inspected 100 times, right? As you can see down there, right? So you can basically add that symbol to it. Okay, and by the way, there are more symbols if you want here, right? But you see here, these are for geometric symbols, and you might be able to find something for that vertical wall, but to me, that wall that I did with that simple I, that is good enough. Okay, so to me, this is appropriate. Now, another thing that you might see is in technical drawings, you might see a circle next to a dimension like you can see over here. If you see next to a dimension, there is this circle and a number, that means that dimension has to be inspected. So in SolidWorks, it's basically this, you put the dimension inside this elongated ellipse, right? Elongated circle or ellipse or a slot. Another way is they put that circle next to the dimension, and that means they have done measurements and it's inspected. So here, if I want to show you this simple example, so here I want to inspect this diameter, which is 500 thous plus 0 and minus 2 thous. I want to know whether this part is made to the dimension or not. I want to provide a report, basically. And so I come here and measure the diameter of this part with the caliper or any other device, CMM machine or something, in several locations. And let's say these are these 4 measurements that I get, these 4 local measurements. And using those 4, of course, the maximum diameter and the minimum diameter, as you can see, are these 2 numbers, using which I can basically calculate my what we call the mated envelope, right? This yellow part, which is like the minimum cylinder that this shaft is going to fit into. And that is clearly, in this case, less than the MMC, which is 500 thous. So it's good. And then the smallest size that I can have is 500 minus 2, so it's 498. And the smallest dimension I have is 4991. So you see, both the min and the max of my measurements are within the MMC and LMC, and therefore I can say both of my measurement pass. So this is, in terms of just diameter, this is a good shaft. Now here we have not added anything for the straightness of the axis or something, but if it's just the measurement of the diameter, this has passed, and we can provide a table like this. We have the ID number. This 1 is this number here, the number of the point that, or the dimension to be measured. And then we can provide MMC, LMC, the measured values, and then whether there is a pass or fail. We can add comments here, right? So you see, for example, as I said, 0.5 is the mating envelope and so on, right? Now, when you want to inspect for GD&T for these tolerances, it's a little bit more complicated. and that's what I want to focus in this video. So here on the left, I have the CAD model of this part that has 2 pins at 4 and 5 and 3 holes 1, 2, and 3. All basic dimensions are given. I have 3 datums A, B, and C, as you can see. And I have provided the position tolerance for the pins, and I have provided the position tolerance for what? For the holes. And now when the part comes out, it comes out like this one at the bottom with, again, exaggerated deviations and exaggerated imperfections. And these are the measurements that I make corresponding to what? Corresponding to those basic and other dimensions. So now with those, I want to see whether these 2 position tolerances for the pins and these 3 for the holes, would they pass or would they fail? So what should I do? Well, let's go one by one. So if you look at hole number 1, this one, okay? First thing is, let's take a look at the MMC size of that, right? Why should we care about the MMC? Well, because here, if you look for these 3 holes, their position tolerance is given at what? At MMC. And they're all the same size, so the MMC for all of them comes from this dimension here. It's 16 plus 0.8 minus 0.2. And for a hole, if you remember, the MMC is basically what? Max material condition is the smallest hole that you can make. So it's 16 minus 0.2, so it's what? 15.8. And it's the same for all 3 holes. And that's what you can see here. 15.8, this is the MMC for holes 1, 2, and 3, okay? Why do I need it? Because now based on what the hole is actually made, based on the diameter that the hole is actually made, I can get some bonus tolerance. Because at MMC at 15.8, the tolerance that I have is 0. There is no room for error when they are made at 15.8. But are they made at 15.8? No. If you look, this hole number 1 is made at 16.1, hole number 2 is 16.5, and hole number 3 is 16.2. So these are the actual sizes, which you can see over here. And then the difference between these dimensions and the MMC will be added to the allowed tolerance, which is 0. So here 16.1 minus 15.8, that's 0.3. Add 0.3 to that 0, it's going to be the same 0.3. 16.5 minus 15.8, that's 0.7. Again, plus 0, that's the same 0.7. 16.2 minus 15.8, that's 0.4, plus 0 is what? 0.4. So these 3 numbers are coming from what? Those bonus tolerances. So this is the amount of allowed position deviations. This is the best I can be off for the center of these 3 holes, 0.3, 0.7, and 0.4. Now, in reality, how much am I off? Let's take a look. So if you look at hole number 1, the dimensions that are given for hole number 1 is this 30 and what? 25 for the offsets. Now, in reality, what I'm measuring is 30.15 and 25.04. So if I subtract 13.14 minus 30, you get 0.14 positive for X. And if I subtract 25 minus 25.04, I get negative 0.04 for the Y. You might say, why is the Y negative and X is positive, right? Because X here, right, my X is measured this way. And so here, the actual measurement is to the right of the basic dimension. So this error, this deviation in general is what? This is the actual measurements, right? Minus what? Minus the preferred dimension, or minus the nominal or basic dimension here. So what is it? In this case, I have a 30.14 minus 30, that's 0.14. Now what about this case? Well, if we go with the same formula, you might say, well, 25.04 minus 25, that should be positive 0.04. 0.04. Why is it negative? Well, because your y-axis is upward like that. So that deviation is in the negative. So actually, it's not 25.04. It's what? It's negative 25.04 minus 25, which is going to be negative 0.04. Okay, so that's why you see a negative in this table. Okay, now that I got my x and y deviation, how much is my actual deviation? Well, if you remember from position deviations, the position deviation is what? The deviation is going to be delta x squared plus delta y squared under the square root, and this is going to be the radial offset. So in order to get a diameter offset, we have to multiply by what? By 2. So this is what? This is the actual deviation that you can see, or the actual position in this case. Okay, this is actual position offset. So this is the formula that has been used here. If you do that, plug those numbers into it, you get what? 0.291. Is that less than the allowable 0.3? Yes. So I'm going to what? Accept it. So I say hole 1 is made in the right position. Now, what about the size of the hole 1? Is it also made in the right size? Yes, because 16.1 is between these two limits. It's between 16.8 and what? 15.8, right? As you can see here, the limits are 16.8 and 15.8. So hole 1, both diametrically and position-wise, is good. Now, whether the profile of it is good or not, that's not what we are checking right now. Let's do a similar thing for hole 2. So if you look at hole 2, right, remember hole 2 is here. The dimension of it again is within the limits. That's good. What about the position of that? Well, let me do a little bit of cleanup here so we can see better. So if you look at hole 2, the dimensions that you need for hole 2 are what? So the x dimension, the x offset for hole 2 is 70 plus 30, so that's 100 from this corner, and then from the top edge is 25 plus 25. So it's 100 in this dimension and 50 in the other dimension. Now, what do we have for it in reality when we did the measurements? Well, if you look here for the x of hole 2, right, this is hole 2, and if you look, it's 100.3, so subtract it from 100, you get 0.3, as you can see. And then for y of this, if you look, that's this measurement, 50.16, subtract it from 50, and you should get negative 16. And again, if you plug these two numbers into that actual position offset, you will get 0.688. And again, is this number less than the allowable 0.7? Yes, so hole 2 is also made in the right position with the right diameter. And then we go to hole 3. For hole 3, again, let me do a little bit of cleaning here. For hole 3, if you look, first of all, the diameter that the hole 3 is made, if you see, is 16.2, which is again between those 15.8 and 16.8, so it's good. Now, what about the location of that? So in this case, you see that I have a 25 plus a 50, so that's 75 around in the y direction, and for the x, it's the same 30, right? So 30 and 75, what do I really have for it? In the x direction is 30.30, so subtract it from 30, you get positive 0.3. And in the y direction, you see it's exactly 75, which it should be 75, so the deviation is 0. Therefore, plug them into the formula and multiply by 2 in that square root, so you get 0.6. And this is, in this case, bigger than 0.4, so hole 3 is drilled wrong. Okay, the dimension of it is good, but the position of it, it's too much off. Okay, and the reason for it is it's made close to the nominal dimension, but the x deviation of that is too much. Okay. So in order to fix that, we have to maybe make this hole a little bit bigger. I mean, as long as we are less than 16.8, we are good, huh? So here the deviation is 0.6. So this number has to be bigger than 0.6. And let's say, for example, if this number was 0.7 instead of 0.6, I would have been fine. But how would it make it 0.7 when the number, as you can see, is to be made 16.5? So if this hole, instead of 16.2, it was made 16.5, which is still between the upper and lower limits, I can pass the hole. So I don't need to redo the part from scratch. All I need is to make the hole a little bit bigger. So you see, that's the idea of bonus tolerance. I'm allowing, by deviating from the MMC dimension, I'm allowing for what? I'm allowing for a little bit bad drilling or offset drilling to be still what? Accepted. And remember that we use this MMC when we have clearance holes. So the pins that are going into these holes or whatever goes into them is clearly smaller than them. That's why we can have this MMC and the bonus tolerance. Okay, let me show you one other example. So far we have seen a single dimension, how to check it and accept or reject it, how to look at the position tolerance, and whether to accept or reject a position tolerance. And now we're going to look at some other examples. And this time we're going to look at profile, angularity, and parallelism, flatness, and perpendicularity. So here we're going to look at some other forms of geometric tolerance with some measurements here, and we're going to see whether to accept it or reject it. So here, as you can see, I have a bunch of points for measurements. One is datum A, so one is the entire bottom surface. Two, as you can see, is datum B, the back surface. Three, as you can see, is datum C, the right-hand surface. Then 4 and 5, both of them are for the slope. 6 and 7, if you look at them, they are for the left surface. 8 and 9 are for this surface, right? So we need to check all of these for all sorts of geometric tolerances. And what I have here are some measurements, okay? And the measurements I have are only for 3, 4, 6, and 8, not for all of them. I have some measurements for 3, 4, 6, and 8, and I want to know whether 3, 4, 6, and 8 are going to be accepted or rejected, and this is my measurement plan. So I have measurement plan to measure 3 in 4 locations, measure, for example, 4 in 6 locations, 6 in 4 locations, 8 in 4 locations. So you always come up with a measurement plan. And now let's say these are some of the measurements that you have for some of these geometric tolerances, and you want to see whether to accept it or reject it. Okay, so let's go for it. So let's first focus on 3. Okay, we want to focus on 3. And for 3, which is, as we said, it is basically the right-hand surface, is datum datum C for this guy. In 4 positions that are not shown here, we made some measurements for what? If you look at 3, the measurements are for perpendicularity. Perpendicularity to what? To A and B, and the amount of allowable tolerance is 0.1. So if you look at 3 for perpendicularity, the allowed tolerance is what? 0.1. But now with these 4 measurements that we have, can we really call it to be perpendicular to A and B or not? Well, these numbers are deviations from the base, from the surface. So basically, this surface, when it's made, it is, if this is, let's say A here, right? And this back wall that you don't see is B, this surface, it's not completely perpendicular to what? Perpendicular to C. It's made a little bit like this at angle. And when we measured with respect to the surface that is going to be true surface, true perpendicular, at 4 points, right? So we measured, let's say, something here, we measured here, we measured here, and here maybe. And we measured these deviations, these guys. We measure these deviations. These are those 4 deviations that I have: 0, negative 0.1, negative 0.1, and negative 0.02, or 10 thou, 10 thou, and 20 thous. Okay, and they're all negative, which means they are inside, and so the angle is less than 90 degrees. So am I going to accept it or reject it? Well, if it's a what? If it's an orientation zone, the amount of deviation that you are measuring, which here we call measured value, is simply the maximum deviation minus what? Minus the minimum deviation. Okay? So in this case, the maximum and minimum, if you look at them, they are what? They are negative 0.02 and 0. If you subtract, then the maximum is just 0.02, and clearly this is less than 0.1, so we accept it and we say yes, surface C is perpendicular to A and B, because A and B, we use them before we start measuring these. We set A and we said that back surface B, which you cannot see but it's in the back, right? We set them on the inspection table and on the V blocks, or vertical blocks, not V blocks, vertical blocks, I'm sorry. And then we started focusing on surface C. Okay, so we're going to accept that perpendicularity. Then we look at 4. For 4, if you look, the form of tolerance is what? Profile. With respect to A, B, and C, so you have to fix A, B, and C, and the allowable profile is 0.3. Okay, so you can see that here. Now the measurement I have for 4, the deviations I have for 4 are these set of numbers. Can I say that the profile is really proper or not? So you see I have negatives and I have positives. So some above the true surface, some below the true surface. Now for a profile, the formula is what? It's the maximum deviation in terms of absolute value. The maximum deviation, the maximum absolute value times 2. Why times 2? Because a profile is symmetric. So the profile tolerance zone is what? Is symmetric. So whatever you measure from one side, you have to multiply by 2. But angularity, perpendicularity, or parallelism, these orientation ones, they are only on one side. So the let me add that for you here. The orientation tolerance zones are on one side of the true surface. So in this case, I look at all of these numbers, see where is the maximum absolute value, that's this number, and then multiply it by 2, so I get 0.2. That's still less than 0.3, so that profile is also what? Accepted. Then I go to 6. What is 6? 6 in this case is another profile. So let's look at 6. That's for this surface. If you look at 6, the allowable deviation is again 0.3. It's a profile. And if you look at them, again, you look at the maximum value, which is this. Take absolute value of that multiplied by 2, so you get this one. Again, this is less than that, so it's still accepted. And finally, 8, which is another profile here for this guy. And if you look at 8, again, it's 0.3. And for 0.3, in this case, the maximum value is this multiplied by 2, that's 0.28. Again, less than 0.3, so it's what? Accepted. Okay, so the important formulas to take out of this lecture is, for a profile, the measured value to compare against the tolerance is 2 times the absolute deviation, the absolute value of the maximum deviation. For orientation is simply max minus min. And for a position, the actual value or the measured value that you have here is what? It is this formula that you can see, 2 times the square root of delta x deviation plus delta y deviation, both squared. Okay, so hopefully this lecture was useful to you and you got some idea how to do the inspection on GD&T with some examples. Thank you. See you in the next video.